Welcome my dear students. Myself, A. Venkatesan, Assistant Professor, Department of Mathematics, Sjctnc-Differential. This is a video for differential geometry and it is an Unit 2 Part 1 video. In this video, we are going to see tangent surface, intrinsic equation or natural equation, uniqueness theorem for space curve, fundamental existence theorem for space curve, and some problems based on this topic. First thing, what is tangent surface? The surface generated by tangent line to a curve C is called tangent surface of C. The next one is intrinsic equation or natural equation. So if a curve is expressed without reference to a particular set of coordinate axes, thus the defining equation are called intrinsic equation or natural equation. For example, if a curve is specified in such a way that its curvature and torsion are functions of arc length s, we may write say kappa equal to f of s and tau equal to g of s, which is a natural equation or intrinsic equation. So now we are going to see existence theorem for space curve. Fundamental existence theorem for space curve. If kappa of s and tau of s are continuous functions of real variable s, where s is greater than or equal to 0, then there exists a space curve for which kappa is the arc curvature and tau is the torsion and s is the arc length measured from some suitable base point. Space curve is uniquely determined within the Euclidean motion. So now we are going to do some. Consider this equation. You know the Sjctnc-Differential formula: t dash equal to kappa n, a dash equal to minus tau n dash equal to tau b minus kappa. Instead of the Sjctnc-Differential formula, we replaced the vector t n b vector as alpha, beta, gamma. So we write this the new Sjctnc-Differential formula: d alpha by ds equal to kappa beta, d beta by ds equal to tau gamma minus kappa alpha, and dr by ds equal to minus tau beta. The equation admits unique set of solutions which assume prescribe the value of alpha naught, beta naught, and gamma. So now when s is equal to 0, in particular there is unique set alpha 1, beta 1, gamma 1, which assume initial value 1, 0, 0 by linear independent set form. When s is equal to 0, the second set is uniquely alpha to beta to gamma to 0, 1, 0. Similarly, the unique set of alpha 2, beta, alpha 3, beta 3, gamma 3, the initial value is 0, 0, 1 when s equal to 0. Therefore, by choice we choosing d by ds of alpha 1 square plus beta 1 square plus gamma 1 square. So we will differentiate the term, we will get 2 alpha 1 dash plus 2 beta 1 dash plus 2 gamma 1 dash. So that is equal to 2 into, replace that alpha 1 dash is kappa 1 beta 1 dash is tau 1 gamma 1 dash is minus tau beta 1. So which is equal to 0 because the first term and third term will be cancelled, second term last term will be cancelled. That is d by ds of alpha 1 square plus beta 1 square plus gamma 1 square equal to 0. So which implies that alpha 1 square plus beta 1 square plus gamma 1 square is a constant. At s equal to 0, similarly we can find that alpha 1 square plus beta 1 square plus gamma 1 square equal to 1 for every value of s. That is a constant we are taking here 1. Similarly, we can prove that alpha 2 square plus beta 2 square plus gamma 2 square equal to 1. Alpha 3 square plus beta 3 square plus gamma 3 square equal to 1 for any value of s. And also we can choose the space curve with this multiple cases d by ds of alpha 1, alpha 2, beta 1, beta 2 plus gamma 1, gamma 2. That is d alpha 1 by ds into alpha 2 plus alpha 1 into d alpha 2 by ds. So similarly, the differentiation with respect to the second term, d beta 1 by ds into beta 2 plus beta 1 into d beta 2 by ds plus gamma 1 into d gamma 2 by ds plus d gamma 1 by ds into gamma 2. So again we simplify the term. Again we apply the Sjctnc-Differential formula, which is also equal to 0. So that is, we can say alpha 1 alpha 2 plus beta 1 beta 2 plus gamma 1 gamma 2 equal to some constant. Similarly, we can prove that alpha 2 alpha 3 beta 2 beta 3 gamma 2 gamma 3 equal to 0, and alpha 3 alpha 1 beta 3 beta 1 gamma 3 gamma 1 equal to 0 for any value of s. Thus, we have the 6 relations given by the equation 2 and 3. Thus, there are 3 mutually orthogonal unit vector. One is t vector, n vector, and the b vector. This t vector is alpha 1 beta 1 gamma 1, n vector is alpha 2 beta 2 gamma 2, b vector is alpha 3 beta 3 gamma 2. Defined for each value of s, we may write this r vector is equal to integral 0 to s t vector into ds. That is r vector equal to r of s. So that is, the r vector is the position vector of any point on the curve, t is a tangent vector, n is a principal norm, and b is a binormal, kappa is curvature, and tau is a torsion of as arc length. So which is clearly says that the existence is required to the curve. So now we are going to prove the uniqueness of the theorem. So now we have proved existence. Curve will be kappa and curvature and torsions are exist in any space. So if they are exist, now we are going to prove they are unique. So at the sense we are taking the two set of curve. Let us choose the two curves C and the C1. So in both the curve, the curvature and torsions are equal same value of S. Now let us choose the suffix only difference. So that is, we will choose the parameter T and P. So it depends on T and P, we may write d by ds of T dot T. So we will simplify this equation because we differentiate that one dt by ds into d1 plus d dot t1 by ds. And then we apply the Sjctnc-Differential formula cases t dash dot t1 plus n dash dot n1. So we will get the value equal to kappa into n cap dot t1 plus kappa into t dot n cap. Similarly, we find differentiate d by ds of n cap dot n1 equal tau into b cap minus kappa t into n cap plus n cap into tau p1 minus kappa into t. So that is, tau is constant, take outside b vector dot n1 minus kappa take outside t dot n1, tau we take outside n dot p1 minus n dot t1. Similarly, we find the d by ds of b dot t. Now we are adding these three above equations, will get equal to 0 because d by ds of t dot t1 plus n dot n1 plus b dot t1 equal to 0. So which gives t dot t1 plus n dot n1 plus b dot t1 equal to constant. So if C is moved in such a manner that the 2 points on the C and C1 corresponding to S is equal to 0 coincides. At S equal to 0, T and P, T1, N1, B1 coincide. So we can write this as T equal to T1, N cap equal to N1, and B cap equal to B1. So possibly we write this equation for us, T dot T1 plus N dot N1 plus B dot B1 equal to 0. But the sum of the cosines is equal to 3 if each angle is 0 or it is an integral multiple of 2 pi. At all corresponding point they be equal, therefore we write T cap equal to T1, N cap equal to N1, and B cap equal to B1. So that is, they simply write that T by TR by ds equal to TR1 by ds. So this is, we may write d by ds of r vector minus r1 vector equal to 0, and which is r vector minus r1 vector equal to a constant vector. So we simply say that one is a vector. So in all the s values it will be equal. So which is gives r vector equal to r1 vector and r vector equal to r1 vector at all corresponding. So therefore the two curves coincides or the curves are concave. So what it says, the theorem, for any space curve, the curvature and torsions exist. If they are exist, they are the unique. So that is the theorem says for these two. So now we're going to solve a problem using the curvature and torsion. Show that the intrinsic equation of the curves given by x is equal to a e power u cos u, y equal to a e power u sin u, z equal to b e power or kappa equal to square root of 2a by 2a square plus b square whole power 1 by 2 into 1 by s, and tau equal to b by 2a square plus b square whole power 1 by 2 into 1 by s. So R vector is given. So we find the curvature and torsion. We know the formula for curvature and torsion. We are using formula in U. So therefore the curvature is equal to modulus R vector dot plus R vector double dot divided by S dot over 3. So we find R dot here. R dot equal to differentiation with respect to U. So that we get a e power u cos u minus a e power u sin u, a e power u sin u plus a e power u cos u, b e power u. S dot means modulus of R dot. So therefore we are taking the square root of this R dot. So we will get the value square root of a square e power 2u and 2 cos square u plus 2 sin square u plus b square 2u. After simplification, we will get s dot equal to e power u into square root of 2a square plus b square. So s equal to, we know this, we are integrating, we know that s dot. So we simply write s equal to integral d by ds into du. So therefore d by ds is integral minus into plus infinity, d by ds by du we know r dot. So e power u into square root of 2a square plus b square into du. So now we integrate the term, we will get the values s equal to e power u into square root of 2a square plus b square. So what it says that both s dot and s's are equal. So this clearly says that the existence of space curve. So now we consider that r dash, we may write r dr by ds equal to r dash. R dash is replaced in terms of u. Dr by du into du by ds. That is, we write r dot by s dot. So 1 by s dot into r dot. So that is, we simply write it 1 by s into r dot value a e power u cos u minus a e power u sin u, y coordinate a e power u sin u plus a e power u cos u, minus z coordinate b e power u. So after expansion, we will get r dash value. Similarly, again we will differentiate the second term. So we will get r double dash value. Again we will change the parameter in terms of the s. And we multiply the term. After simplification, we will get the term s cube into r double dash plus r triple dash value. And finally, we calculate, we get s cube into r double dash plus r triple dash equal to 1 by 2a square plus b square into 0, 0, 2a square. So using this one, now we are going to find the curvature. So t dash equal to r double dash, kappa t dash is kappa n equal to r double dash, kappa n equal to r double dash. How we are finding where there goes equation, sixth equation, 1 by s into this one. So we need kappa, so therefore we are taking n dot product into itself. Therefore kappa square, kappa into kappa, kappa square, we are taking dot product again itself. So therefore that is equal to 1 by s square into 1 by 2a square plus b square into 2a square. Therefore kappa equal to square root of 2a divided by square root of 2a square plus b square into 1 by s. Similarly, we can find the torsion of the same curve. The torsion is b by 1 square root of 2a square plus b square into 1 by s. Thanks.